I will be talking about the article Abiogenesis, the Carter Argument Reconsidered by Daniel P. Whitmire. As the title suggests, the article discusses the Carter argument. I excuse myself for my voice. I am unfortunately sick. You may also notice cuts throughout, as I cannot talk for longer periods of time, and I do not want to redo the entire presentation every time I mess up. The Carter argument, as Carter formulated it in his paper, The Anthropic Principle and Its Implications for Biological Evolution in 1983, suggests that life existing on Earth is insignificant in terms of probability of life occurring on Earth-like planets in general. To prove this, he uses the Bayes theorem, which I will explain shortly, to show that the probability of abiogenesis being easy, if we take into account that life on Earth exists, is the same as the prior probability of abiogenesis being easy without considering any evidence at all. Whitmire challenges this, saying that the Carter argument suffers from a flaw called the old evidence problem, which was formulated by Clark Glimmour in his book Theory and Evidence in 1980. Whitmire then uses the Bayes theorem to prove that life on Earth is not only relevant to the probability of easy abiogenesis, but even a sign that abiogenesis is likely on Earth-like planets at some point during their habitable period. Carter first formulated his argument in 1983 with the help of the Bayes theorem. The Bayes theorem is a method to update the probability of a hypothesis by taking into account newfound evidence. As you can see, the probability of you being at the sea, given that you just picked up a seashell, depends on the probability of you picking up a seashell, given that you are at the sea, the probability of you being at the sea in the first place, and the probability of you picking up a seashell regardless of where you are. We put these values in a nice little formula and get the probability of you being at the sea, given that you just picked up a seashell. In Carter's case, the equation is a little different. He wants to calculate the probability of abiogenesis being easy, given that life on Earth exists. If you remember our previous calculation, he will need the probability of life on Earth existing, given that abiogenesis is easy, the probability of abiogenesis being easy prior to life on Earth existing, and the probability of life on Earth existing regardless of whether or not abiogenesis is easy. He also uses the neat little trick that the probability of life on Earth existing, regardless of whether abiogenesis is hard or not, can be replaced with this term here. Now you may have spotted that we are assuming that abiogenesis can only be either hard or easy, otherwise our term here wouldn't work. This means we are excluding any possibility that abiogenesis is just moderately challenging, but Whitmire defends Carter here and argues that a binary approach is perfectly sufficient. By definition of the Bayes theorem, Carter's starting equation looks like this. Using the undisputed fact that life exists on Earth, the probabilities for life on Earth existing, giving any other evidence, or none at all, are all equal to 1. And since Carter is using a binary approach, the probability of abiogenesis being easy plus the probability of abiogenesis being hard is equal to 1 as well. Thus he ends up with this equation here, proving that the probability of abiogenesis being easy is completely independent of the fact that life on Earth exists. The same proof can be conducted for abiogenesis being hard, leaving him with the fact that the argument that life on Earth exists has no influence on the difficulty of abiogenesis in general, and is therefore irrelevant for the discussion on whether or not life on other Earth-like planets is likely. But why was this relevant for the discussion in the first place? Up until Carter, the historically accepted argument for easy abiogenesis was the principle of mediocrity. This argument comes from philosophy and establishes that everything happens according to natural, universal laws. Everything is perfectly ordinary, and so everything that happens is likely to have happened. None of us can escape these laws, and we are therefore not extraordinary or special in any way. This philosophical theory does pose a few pitfalls that need to be navigated. The principle of mediocrity clearly distincts the term special from the term unique. As an example, there are almost 9 million people in Switzerland, but according to the law of mediocrity, none of them are special. Each one of them was created by chance. Their appearance is based on the shuffling of genetics. Their history is comprised of a series of coincidences, and their current state is the result of a network of probabilities. All of this makes every single one of them unique. Their combination of appearance, gender, character, social status, personal experience, culture, opinions, and so on is unique to them. Their unique combination has never occurred before and will never occur again. Looking at genetics, we are all incredibly similar. We share more than 99% of our genome with any other human on the planet. This makes us virtually identical when it comes to the things we need to survive. We all need the same nutrients, need to drink water regularly, breathe, sleep similar amounts of time, and our bodies have similar constraints when it comes to physical capabilities. As we can see, there are universal laws that define us as a human. However, preferences and opinions define each one of us as unique. I love tomatoes and paprika, but I hate onions. I prefer milk to water and water to anything else. My sleeping schedule is far from ideal, but I get enough rest in the end, and I enjoy sports, but I am not very good at them. All of this will likely differ from your preferences and dislikes, which makes you and I unique in a sea of equally unique humans. Nothing special, but distinct enough from everybody else to be recognizable. To sum it up, nobody is special, but everyone is unique. Some differ more than others, but we are all human and bound by the universal laws that all humans have to follow. Applied to our planet and the life it is home to, we can deduce the following. Life on Earth is not special. It evolved due to a series of coincidences that could have happened anywhere else with similar possibility, provided the planetary environment was somewhat similar. Since life on Earth exists, and we know of other planets that we can categorize as Earth-like, there is no reason to assume intelligent life could not have very easily evolved somewhere else in the universe. However, Earth is unique, and the life it harbors is too. So while we are not special as an occurrence, in the universe our appearance, customs, and requirements very likely are unique to us and us alone. According to an article by Seth Shostak called Extraterrestrial Intelligence, the principle of mediocrity in astrobiology goes back to Nicholas Kepler and states that the properties of our solar system and planet are not unusual in any important way, which consequently leads to the assumption that the processes on Earth that led to life and eventually intelligent beings could have occurred throughout the cosmos. Paired with the fact that life on Earth occurred relatively early on during Earth's habitable period, this is widely accepted as a strong argument for easy abiogenesis. In his paper in 1983, Carter not only refused the fact that life on Earth exists as a valid argument for the discussion, but also concluded that the average timescale for intelligent observers to evolve is larger than the solar lifetime, and in turn that Earth is not an average example of Earth-like planets, all of which is a counter-argument to the principle of mediocrity. However, Whitmire notes that despite the logical appeal of the Carter argument due to its foundation in mathematics, the general notion of the scientific community is still optimistic towards easy abiogenesis on Earth-like planets. Whitmire attributes this to the counterintuitivity of Carter's conclusion. While not founded in mathematics and logic, the principle of mediocrity is still more appealing, and for good reason. Whitmire challenges Carter's dismissal of life on Earth as valid evidence due to the so-called old evidence problem. Bayes' theorem is used to update a probability when new evidence is found. If the evidence already exists, and we use that fact to set its probability to 1, then the probability of the hypothesis does not change after the evidence is introduced, and the Bayes' theorem becomes useless. Here is an example. We toss a coin 50 times, and it always comes up heads. We want to calculate if the coin is fair, given the evidence that we threw 50 times heads prior to our calculation. To do this, we use the Bayes theorem, and since our evidence has already happened, we set its probability to 1. You can already see how this could be problematic. Since we have a binary system, the probability of the coin being fair plus the probability of the coin being unfair is 1, and we are back at Carter's conclusion, namely that our evidence of the coin coming up 50 times heads has no influence on whether or not the coin is actually fair. Assuming a prior probability of 0.5 for the coin being fair, this leaves us with the conclusion that the coin has a 1 in 2 chance to be fair given the evidence. This is obviously not true, but it illustrates very nicely the problem we are facing here. This example is taken from Grimoire's book, in which he suggests to apply Bayes' theorem historically, meaning at a point in time where the evidence was not yet known. Using this, we change the probability of our coin coming up heads every time, given that the coin is fair, to its actual probability of 1 in 1 quadrillion. Then our calculation looks like this. Notice that the probability of 50 heads, given that the coin is unfair, stays at 1. This is arbitrary. In our case, we assume that an unfair coin has heads on both sides, making it impossible to throw tails. With this calculation, our probability for a fair coin, given the evidence, becomes 1 in 1 quadrillion, which is almost 0. Another example would be the following. Imagine we have two urns, A and B. One of these urns contains 10 balls labeled 1 to 10. The other contains 1 million balls labeled 1 to 1 million. We pull a ball from urn A. The ball is labeled 7. What is the probability that urn A is the one with only 10 balls? If we follow the principle of mediocrity, then intuitively, urn A is the one containing 10 balls, since then the ball number 7 would be typical for the balls in urn A. We now apply Bayes' theorem to this problem and get the following equation. If we use the old evidence and set the probability of pulling ball number 7 to 1, our probability of urn A being the one with 10 balls, given that we pulled ball number 7, is equal to the prior probability of urn A being the one with 10 balls, given no evidence at all, which is 1 in 2. The correct approach would be considering the evidence historically. The probability of pulling ball number 7, given that urn A has 10 balls, is 1 in 10. The probability of pulling ball number 7, given that urn A has 1 million balls, is 1 in a million. And if we pop these probabilities into our equation, we get a probability of almost 1. So pulling a ball number 7 out of urn A is almost a guarantee for urn A to have only 10 balls. In these two examples, the old evidence problem is easily resolved, but Mittmeyer lists a couple of cases in astrobiology which weigh old evidence as equivalent to new evidence and are not as easily rectified. He notes two prominent examples. The precession of the perihelion of Mercury is the phenomenon where Mercury's closest point to the Sun on its elliptical orbit shifts over centuries because of tiny gravitational influences from other planets. This was universally considered strong evidence for Einstein's general theory of relativity, despite having been known for 50 years before Einstein's publication. Similarly, Newton's law of gravitation states that any particle of matter in the cosmos attracts any other with a force proportional directly to the product of their masses and inversely to the square of their distance to each other. This explains Kepler's laws of planetary motion, despite being over 50 years older. Whitmire argues that from a physics perspective, these examples are completely justified because the theories were formulated independently from the data they are explaining. Generally speaking, the problem of old evidence is more complicated the more philosophical things get, but there is some leeway. Whitmire then concludes that the Carter argument fails due to the old evidence problem. In Carter's calculations, he assumes that the probability of life on Earth existing, given that abiogenesis is easy, is the same as life on Earth existing, given that abiogenesis is hard. Whitmire argues against it with the argument that intuitively, the probability of life on Earth existing, given that abiogenesis is easy, should be higher than the probability given that abiogenesis is hard. He concludes that this is a major oversight in Carter's argumentation, and that the Carter argument should therefore be revisited with the updated probabilities. Whitmire uses an analogy to demonstrate. The conception of me could have occurred if my parents used contraception. Conception is hard, CH, or if they did not, conception is easy, CE. Given the evidence that I exist, what is the probability that conception was easy? As in the Carter argument, one could say that I exist regardless of whether or not conception was easy, and thus my existence does not alter the probability of conception being easy whatsoever. But as we saw in the coin flip example, this is not the correct approach. The probability of me existing now does not matter. What we need to consider is the probability of me going to exist, given whether or not my parents used contraception. Assuming the probability of conceiving without contraception is 0.85, the probability of conceiving with contraception is 0.01, and the probability of conception being easy is equal to the probability of conception being hard, so 0.5, then the probability of conception being easy, given that I was conceived, is 0.99, so very close to 1. Whitmire now considers the two binary options, abiogenesis is hard and abiogenesis is easy, and takes into account the fact that the probability of life on Earth appearing, given that abiogenesis is easy, is higher than the probability of life on Earth appearing, given that abiogenesis is hard. To approximate the probabilities of easy and hard abiogenesis, Whitmire uses a timescale argument. If two timescales use completely different physics, there is no reason on why they should be comparable. Generally speaking, if two timescales, for example a human lifetime and the lifetime of a star, depend on different natural laws, like biology for the human and nuclear physics for the star, then one of them is likely to be a lot smaller than the other. Whitmire uses this to define that the timescale of abiogenesis is a lot smaller than the timescale of Earth's habitability, since abiogenesis depends on pre-biological chemistry and the habitability of Earth on nuclear physics. Furthermore, he adopts the two as the natural definitions for the prior probabilities of easy and hard abiogenesis, since these two are the expectations prior to life on Earth. He then concludes that the probability of easy abiogenesis has to be much greater than the probability of hard abiogenesis due to the probable notion that the habitability timescale of Earth is much greater than the timescale for abiogenesis. In terms of the conception analogy, if the time frame for a woman to conceive is 35 to 40 years, but the time frame for the actual process of conceiving is way smaller, then there are a lot of possible moments where she could become pregnant and have a child, making having a child a very likely outcome. To sum this up, the probability of life on Earth, given that abiogenesis is easy, is higher than the probability of life on Earth, given that abiogenesis is hard. We are assuming a binary system, so the probability of abiogenesis being hard plus the probability of abiogenesis being easy is equal to 1. Due to our timescale argument, the probability of abiogenesis being easy is a lot higher than the probability of abiogenesis being hard during Earth's habitable period, which concludes that at some point, the probability of abiogenesis being easy is very close to 1, while the probability of abiogenesis being hard is very close to 0. If we now use Bayes' theorem, we get the following. As you can see, this proves mathematically that the probability of abiogenesis being easy, given that life on Earth exists, is very close to 1 at some point during the habitability period of an Earth-like planet. Now, this calculation would technically only prove abiogenesis for a precise Earth-like twin, but Whitmire makes the assumption that it also applies to the vaguer notion of Earth-like planets in general, given some leeway. In conclusion, Whitmire has argued that life on Earth cannot be dismissed as evidence during the discussion for abiogenesis on Earth-like planets. Using this and an independent timescale argument in conjunction with the Bayes theorem, one can prove that given the evidence of life on Earth, abiogenesis is likely at some point during the habitable period of an Earth-like planet. I do not think further research is the right word, but the paper is very thought-provoking. I do feel that maybe a middle way should be considered. Abiogenesis could just be slightly hard or fairly easy, and not incredibly likely or incredibly unlikely, as the article suggests. Also, if we are speaking on the principle of mediocrity, if we apply it to abiogenesis, then shouldn't abiogenesis not being special mean that it's neither exceptionally hard nor exceptionally easy? The paper ends very abruptly, and I was a little perplexed. He took a lot of time explaining the old evidence problem, but when it came to the timescale argument, he seemed to almost brush over it. It felt like he himself saw his second argument as weak and that it wouldn't hold up, so he spent a lot of time to make his first one stick. It also led to me not fully understanding his argumentation, at least in the second half, with the timescale argument, which only contributes more to the weak appearance of this argument. The paper was already quite short. I feel like he could have elaborated more on the complex part of his argumentation. I did, however, thoroughly enjoy reading the paper. It uses a lot of examples and analogies, and it is very easy to understand for a non-natural scientist. I always enjoy when science crosses into philosophy, and this article was pleasant to read. It also felt like the author shared my enthusiasm and that he had a lot of fun writing it. Also, just going through additional research on certain philosophical topics made me realize how much philosophy still is part of astrobiology, and I'm very, very much looking forward to reading more on it in the future. Yes, but thank you for watching. Put any questions into the comments, and I'll see you there.